looks like everybody's just about set. So before I actually start talking, how many people believe, of all of you, who believes that there is life elsewhere in the universe? Now, hang on. When I'm talking about life, I'm not talking about blue-green men. We're talking about any kind of life. Bacteria, algae, anything, any kind of life. How many people believe there is life elsewhere besides the Earth in the universe? And keep your hands up. How many people believe there is life elsewhere in our galaxy? How many people believe there is life elsewhere in our solar system? Few. Okay. My goal, and I have to give you a disclaimer. I can't prove it to you yet, but there is increasing data to support the fact that there is life elsewhere, not only elsewhere in the galaxy, can't say the universe, but elsewhere in the galaxy, but even in our own solar system. And my goal is to try and convince you. So this is one of humankind's primary questions. The other one being, how did we get there? How did the universe start? How did Earth and the solar system start? But the one that many of us question, and it's the burning question in my mind, is, are we alone in the universe? And there are two things. One, we can talk about intelligent life. And a better term for that is sentient life, meaning self-awareness. And then any type of life. And I'm going to talk a little bit about sentient life, but mostly going to talk about any kind of life elsewhere. So in terms of intelligent life, no, we're not talking about either of these, because we don't know what they're going to look like if they are up there. But we have been actually looking for intelligent life for quite a bit of time. The evidence we are looking for so far is based on SETI, which is the search for extraterrestrial intelligence. And again, we're talking mostly about sentience. And these are radio telescopes on Earth that are looking for either repeated signals or signals in patterns. There have been a lot of hits where we think maybe there's something, but nothing has panned out so far. And it's been ongoing for more than 20 years. So we can't answer the question yet. We don't have direct evidence of life anywhere else. But we're looking for some biologic signatures. Some of it's evidence of carbon dioxide or oxygen, especially oxygen, because oxygen is prominent in a planet's atmosphere if there is with chlorophyll that turns carbon dioxide into sugar, with oxygen being a byproduct. And we're also looking for evidence of carbon molecules, organic molecules. The other thing we are looking for is evidence of habitability. And habitability means that you have to have three things present. One is persistent, either liquid water or liquid something else. So far as we know, it's just water, but there may be other things, and I'll talk about that. You need to have the key chemical ingredients of life, the key atoms. So carbon, oxygen, hydrogen, sulfur, phosphorus. These are the things that allow you to use energy to live and reproduce, and that's a function of life. And then you have to have some kind of energy for metabolism. And we think of energy being always the sun. That's not always the case, and you'll see what I mean. So we've been looking in two different areas. One is around distant stars. We're looking at exoplanets specifically, where there are planets that orbit another star. And we're also looking in our own solar system. So let's take stars first. There are probably And this is a way underestimate. We're probably now thinking should have it as a TR instead of a B. We're thinking that there is 1 trillion or 2 galaxies in the universe. Now that we've had the James Webb Space Telescope, we've seen that the number of galaxies is immense. There are about 300 billion stars in our own Milky Way, and our Milky Way is just an average kind of galaxy. And so the conclusion is that there's 3 times 10 to the 22nd stars in the universe. That's more than all the grains of sand in all the beaches, oceans, and all on Earth. You can't count it. It would take you millions of years to count the number of stars there are in the universe. So there's a very good possibility of life elsewhere. We know that, statistically speaking. We just haven't found ones close enough. Is the problem. So far, there are more than 5,000 exoplanets that have been discovered. It's now up to about 5,600, I believe. So how do we find exoplanets, planets around other stars? There are 3 ways. Radio velocity, but that only tells you there is a planet and where it's located, and basically how big it is. It doesn't say anything about the planet itself. Then there's a thing called transit, and then direct imaging. And those latter 2 can tell us information about what the planet consists of, at least the atmosphere. Radio velocity is looking for Doppler shifts. As I said, it only gives us the planet's mass, and there's no information about the atmosphere. And if you look, this is a planet orbiting, let's say, another star. And you see, as the planet goes around, it makes the star wobble a tiny little bit. And we can see that Doppler shift and measure it. And that allows us to tell how big the planet is and how close it is to the star. Yeah.
Okay. My question: the speed of light is always the same.
Right.
How can you have Doppler shift?
Because of the fact that the same way you have Doppler shift with sound.
Sound is different.
Well, sound is different. But as the object moves closer or away from us, it changes the frequency of light that's being delivered. So if you have a yellow star and it's moving away from us, it looks red. The speed of light is the same. It takes the same amount of time to get to us, but it just has a different frequency in terms of what it looks like. So then transits occur, again, when a planet moves in front of a star. But now we can measure the change in brightness of that star as the planet passes in front of it. Okay. The dip in brightness is at maximum 1%, so it's tiny. But there are sensitive enough satellites that we have up that give us the information that the star has dipped in its brightness. And that tells us how big the planet is, how close it is to the star. But also, because we have spectrographs, it can tell us also what kinds of molecules are in the atmosphere. And again, you see the planet orbiting the star. And as it comes around, it casts a shadow in front of that star, and that makes a dip in the amount of light that's coming to us. And one of the satellites we have up that's been doing a lot of this work is NASA's Transiting Exoplanet Survey Satellite, and it's specifically designed to look for exoplanets. And you can see on the left-hand side that dip in brightness coming out of the star. And you see if 1.000 is 100%, it goes down to 0.970. So it's less, it's only about 0.03% of a dip. But it's still enough to be able to be seen by these sensitive satellites. And then the direct way is direct imaging. So you can take photographs of exoplanets if you have a big enough telescope, and you can do spectrographs of those planets if you have a big enough telescope. The problem, though, is if you look on the left-hand side, this is what we're doing. You're looking at a sun, let's say a star that looks like the sun, and let's say we're looking at a planet the size of Jupiter, so the biggest planet in the solar system, and let's say it's close to its star, so it's hot. Or even worse, in terms of trying to find it, an Earth-like exoplanet, one that's the size of the Earth and cooler. An exoplanet that's near it is 1,000,000 times fainter, whereas an Earth-like exoplanet is about 10 billion times fainter. So on the right, it'd be looking at a lighthouse and trying to find either a firefly near that lighthouse, and there we wouldn't even find anything that could support life, or hopefully one that supports life, one that's looking at like bioluminescent algae in the midst of a lighthouse. It's almost impossible, but we have found a way to do it. This is how it's done. It was called a chromograph. And if you notice, the yellow star in the middle is the star, but you don't see it because it sets up electronically basically like an eclipse. And so the things that are the blue objects going around that yellow star are exoplanets. And we can take pictures of them and also do spectrography of them. And that's especially been useful given the James Webb Space Telescope, which has tremendous capabilities. So now what? We've discovered over 5,000 exoplanets, as I said. How do we take the next step in terms of detecting the planet characterization? The first thing we want to know is, does it have an atmosphere of any kind? What molecules are present in that atmosphere? Could it support life? And then finally, obviously, the question, does it have life? And the last one is going to be very difficult to determine. So in terms of looking for habitability, most of the stars that we've looked at have planets that are too close and therefore the surface is too hot, or too distant and the surface has no liquid water. I'll get back to this later though. We shouldn't just put that aside yet. But there have been actually several hundred planets that are found in the habitable zone. We've looked for signature gases. There's been one planet that we found with carbon dioxide. I'll talk about that in a little bit. None with oxygen so far. So this gives you an idea of where the habitable zones are. If you have a hotter star, the habitable zone is further out. A cooler star, then it's closer in. And then if there's one like our sun, it's sort of in between. So if you look at the bottom, that's our solar system. And you see that Earth sits smack dab in the habitable zone, with Venus on the inner edge and Mars on the outer edge. But if you look at the TRAPPIST-1 system, and this has not been fully explored yet, you can see that basically E, F, and G are all in the habitable zone. We just haven't looked at them yet to see what kind of atmospheres they have. Obviously, B is too hot, H is too cold, but in the middle, there are at least 3, maybe 4, that could be habitable. And in fact, Hubble, even before James Webb, found 30 planets that had water vapor in their atmospheres. The problem was all of these were too hot for liquid water. But it gives us hope that we will find planets with water vapor in their atmospheres where they're in the habitable zone and therefore probably have liquid water on their surface. And this is an image of Mark's conception of the James Webb Space Telescope, which is a whole other talk I have. if you want. But this telescope is the largest space telescope ever produced. Some of the ways we look for life is look for liquid water, look for signs for biologic activity like methane or other biologic molecules, and I'll talk about that. Analyze the reflected light from a planet to see if it has an atmosphere and what molecules it has in the atmosphere, especially oxygen, but some others. And then rule out other explanations. Signs of biologic life. There's this exoplanet that James Webb looked at. It's an exoplanet of a cool dwarf star named K2-18. So the planet is named K2-18b. It's about 136 light years from Earth. It has an abundance of methane and carbon dioxide. And this suggests that it might be an ocean world under a hydrogen atmosphere based on the chemistry. If anybody has questions about that, I'll let Lloyd answer because I don't know. But recently, James Webb found evidence that there is dimethyl sulfide in its atmosphere. Now, dimethyl sulfide on Earth is seen in three situations. One is in certain bacteria. Two is plankton that feed on dead fish. And three is certain marine algae. Dimethyl sulfide is what gives it the fishy smell at the shore, at the beach. It's not seen anywhere else on Earth. It's not any kind of chemical process or anything like that. So if James Webb, and we're not sure about this yet, James Webb is not, the scientists are not completely sure. They need to double check it and make sure they really saw dimethyl sulfide. But if they did, and they have no other explanation, if they don't see any other biological, any other just chemical processes, not biologic processes, that could do this, then that means K2-18b has to have life on it. So we're getting close. I'll also talk about the solar system a bit. There's possible evidence of at least previous ancient life on Mars, and I'll talk about that. There's evidence of habitability in other bodies in the solar system, although we don't have any actual proof of life yet. So what about Mars? The early rovers on Mars had a suggestion of water. They saw outflow channels as well as layers of rock. And layers of rock happens only when you have sedimentation, which means basically free running water. Curiosity confirmed the presence of water. It was present for about 1 billion years until about 3.6 billion years ago. And this is around the Gale crater. And Perseverance confirmed the evidence of water at the Jezero crater. That's the more recent rover. So Curiosity found that the surface around the landing site was made of pebbles and all were sedimentary. And the reason they thought it was sedimentary is many of the rocks and pebbles are rounded, and the only way you get that is due to erosion. Now, wind erosion could do this, but the way they laid together and the way they formed, it was pretty obvious that it was liquid water doing this. And then further away, there's still extensive sedimentary rock in layers that they thought had been there also based on the spectrograph that was on Curiosity. They believed to be low in salinity, that is low in salt, and a neutral pH, which is very conducive to having a habitable environment and was relatively young. So the other findings on Mars were the spectrographic findings, and they did see building blocks of life. Things like carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur. These are the things that are needed to be able to make DNA, to make amino acids, to make atropine sulfate, phosphate, which is the way that energy is transferred. And they also found organic molecules. They found carbon-based molecules that were in a more complex form. And this means two things. Sometimes these happen naturally. We'll get to that. But sometimes, a lot of times, they're biologic in origin, which would mean least ancient life on Mars. And if you look at one of the things that Gale cratered by Curiosity, if you look just below the sky, you see all those layers. That had to be sedimentary formation, which means liquid water running on a regular basis on the surface of Mars. And these are those rounded pebbles that were nearby. Now, one of the things I was always taught was that life happened on Earth somewhere around 1 billion years. It took that long for life to form. We now know from examination of Earth that life formed probably about 400 million years after the solar system was formed. And that means that there was plenty of time for life to have formed on Mars. Perseverance landed in February 21 at the Jezero crater. Its purpose was to look at a river outflow channel and lake, as well as a delta. And these are the best places to look for ancient life because the stuff comes down off the hills and gets deposited there. And so it's been drilling core samples, which are then deposited in titanium tubes stored on the surface. And you see these eroded stones at the landing site where Perseverance was. So the future mission is to return these samples. What's going to happen is the lander will land next to Perseverance. Perseverance will go over and give the lander the samples that have been collected and put them in a container that is sort of re-entry proof, be able to survive re-entry, just like the new satellite. And they will return them to Earth for study. And the plan is to determine if there are organic molecules present. So this is how it worked. You see on the lower right, the sample return lander. On the lower left, Perseverance. On the upper left, the Mars Ascent Vehicle taking off from the sample return lander with the samples intact. And then docking with the Earth Return Vehicle on the upper left, which will then come back to Earth. Now, there are other bodies in the solar system where we think planets might have free water. They're not in the habitable zone. So there's no way they have free water on the surface. They don't have enough energy from the sun to support life. But they, first of all, do have chemicals needed for life in them. And we're now thinking that they have liquid oceans and plenty of energy to support life. Now you're looking at me crazy. But I will tell you this dream. Europa is one of Jupiter's four largest moons. It's actually the smallest of them. But it has about 2 times the ocean of Earth below its ice crust. If you were to measure the temperature above the ice, it'd be about minus 180 or so. If you go below the ice, there is a liquid ocean. It's way out of the habitable zone, but it has this liquid energy, the liquid ocean, so it has some kind of energy. And we've actually seen plumes of water spraying out of cracks in the ice. And it does have a rock mantle with plenty of minerals needed for life. So how does this occur? And this is the surface of Europa. And you see all that brown stuff that's on the surface. That's all organic material that have been pushed out through the cracks in the ice. The reason it has this big an ocean is because there is no landmass to interfere with it. The ocean is fairly deep, like several hundred miles deep, and surrounds the entire planet. So there's plenty of water there. And if you look at the comparison, on the left is Earth, and all of Earth's water is in that little circle of blue. If you look at Europa, which is much, much smaller than Earth, it's less small, it's less the size than our own moon. But if you look at the water that's present, it's almost the whole planet. And this is how it works with tidal flexing. If you just wave your hands around, go ahead, wave your hands. You don't feel anything. Okay. Your hands are still cold because it's cold in here. Now go with this. Your hands are getting warm because of friction. Well, Europa, because of its eccentric orbit around Jupiter, is constantly pushed and pulled by this huge Jupiter. Because of that, it causes tidal flexing, and this basically causes friction that heats up not only the mantle, but the water that lies above the mantle. And that's how Europa has a liquid ocean. So what? I'm going to show you a video of something on Earth. This is one of the hydrothermal vents that's at the bottom of the Pacific Ocean. It's down far enough, 3-4 miles. There is no light. It's just barely above freezing. But there's basic lava and heat coming out from the mantle below. And look what's there. There's all kinds of life in there. Now you look at that and you say, well, okay, so the life was up high and drifted down and got sustained by this. And that may be true to a certain degree. But we've looked at all the life down there. We've gone down there, as you can see, took photos, but also got samples. And some of that life has basically no connection with any other life on Earth. Now, that doesn't mean that it was extraterrestrial. What it means is that life probably originated down at those hydrothermal vents. A lot of scientists now believe that that is perhaps where life originated on Earth, in those hydrothermal vents, not up in the tidal pools, and then migrated up. But at least some of the life originated there. And the answer, and the question I have was, all right, if life originated down into those hydrothermal vents on Earth, where it's almost freezing, where there's no life, the only energy of the hydrothermal vents, we know Europa has them, why not life on Earth? This year, in late summer, early fall, the Europa Clipper spacecraft is going to be launched. Its mission is to arrive at Jupiter in 6 years, orbit Jupiter and Europa, so it lowers the amount of radiation it's being exposed to, and fly through some of those water plumes to detect what's below. Now, NASA will not admit that their goal is to detect actual life. Their goal is to detect, is there habitability down below in those oceans? My thought is, if they detect not only habitability, but they detect all kinds of organic molecules, it's likely there's life down there. And the follow-up mission would be to actually send a robotic probe down into that ocean to see if there is life. I was lucky enough to actually go to JPL and see it being put together. This is a huge spacecraft. It's about maybe 20 feet tall, by about 6 or 7 feet wide. This is the clean room, which is 40 or 50 feet tall. And you can see it looks dwarfed in there, but that's how big it is. So it'll launch in 2024. It'll take 6 years to reach Jupiter. It's going to do about 50 swings past Europa over the next 2.5 years after it arrives. And it's there to determine definitively habitability and looking at the consistency of the ocean, both by radar as well as pictography of those plumes of ocean water. And also look for possible sites for future landers and doing like this. Ganymede is another one of of Jupiter's moons. It's the largest of Jupiter's moons. It has a huge ocean underneath the ice shelf, much, much bigger than even Europa. And it also abuts rock. This is Ganymede. It's, again, an ice world on the outside, but you can see carve it away, and on the inside is this ocean that's huge. The problem with Ganymede is it doesn't have any of those cracks with plumes of water coming in, so we don't know whether it has enough energy to support life. Titan is Saturn's largest moon. It's far beyond the habitable zone. The temperature on Titan is about -250, but it's similar to Europa. Actually, -289. Sorry, I'm misestimating. It has a nitrogen atmosphere just like Earth, but unlike Earth, which has silicon dioxide as rocks, on Titan the rocks are organics and water ice. That's how cold it is. But it does have an atmosphere that has all these organic material in it. This is an artist's conception of what it might look like on Titan with Saturn in the background and liquid methane rivers. So it's cold enough on the surface that most people don't think, even though there's liquid, that there would be enough energy to support life there. But it does have this organic rich atmosphere with cracks in the crust that would allow that organic material down into the water. The question is whether it has enough energy there, because again of tidal heating, to allow for organic life to form. We're not as convinced about that, but the goal is to eventually explore Titan and see if that is a possibility also. Okay, so one of the things to know about is life will exist anywhere in the universe it possibly can. These are tiny, tiny crystals between pieces of ice in the Arctic. Okay, and there's a tiny little droplet of water in there. And you see on the lower right hand slide that basically with fluorescent stain, those are tiny bacteria. So even in this high scale environment, tiny bacteria formed and on there. The other thing that we know is that Surveyor 3, which landed on the moon in 1967, was doing exploration on the moon for 30 months. When Apollo 12 got there, clipped off a piece of the Surveyor to bring back. And scientists wanted to see what was going on. And so besides examining it, they cultured it. And there were staph bacteria that grew. Now that doesn't mean that there were staph bacteria originally on the moon. What it means is that Surveyor had bacteria on it. Had bacteria on the moon for 30 months. And that bacteria is still viable. Still able to live when cultured. Enceladus is one of the smallest of Saturn's moons. It orbits closer to Saturn than Titan does, so more of this tidal heating has geysers with ammonia-rich water coming out of it. So this is Enceladus, and this is an artist's conception of the liquid ocean below it, and you see cracks in the crust where the liquid ocean is spurting out. Now, there's some interesting findings that Cassini had more recently. It was 6 years ago, but more recently than that. And there was large amounts of dihydrogen, which is evidence for hydrothermal vents like on Earth. There was an abundance of carbon dioxide and methane, and there was a new finding of an abundance of phosphorus, which is part of DNA and part of the energy transfer mechanism in living organisms. So there's good evidence that Enceladus, again, might have viable life in those oceans. And NASA has plans for a flagship mission about 10 years from now called the Enceladus Orbital Lander, where there'll be an orbiter and a lander to try and determine that habitability. I talked about the phosphate. Actually, the phosphate's about 3 times as much as in Earth's oceans. Callisto is the second largest of Jupiter's moons. Originally, we thought it was just a dead world, just frozen out as a run. More recent probes like Juno has demonstrated the possibility of maybe an ocean, but the ocean is deeper than it thought, or not present at all. It might be just like slushy ice. So that's probably not one we're going to be looking at in detail, but it's another moon that has some kind of water or ice present. And you can see it in that sort of purplish rim there in between the ice shell and the mantle down below. Uranus and Neptune are the 2 smallest gas giants. They're the planets farthest in the solar system and were only visited by Voyager 2 in the 1970s, so don't have a lot of good information about them. And that's Uranus. And we know Uranus has like at least 5 moons. We don't know anything about them, so whether they could have oceans and tidal heating and evidence of life, we have no idea. But we do know that basically there's an abundance of ocean worlds across our solar system. Earth actually is not an ocean world, believe it or not. It's mostly rock. The amount of ocean is tiny, but it allows us to live and survive in it. All the others have much larger oceans. And finally, there's a question about whether there's life on Venus. The surface temperature on Venus is 900 degrees Fahrenheit and 90 times that the pressure of Earth's, and has clouds with sulfuric acid, so nothing can survive it. But early Russian probes found particles in the clouds that were a micron long, which is the same size as a bacteria on Earth, but it could be just inorganic material. U.S. orbiters found dark streaks in the clouds that persisted even though strong winds, and some people thought they were gnats of bacteria, and they thought it was just radar return from the mountains, the volcanoes on Venus. But the more recent finding was phosphine in those clouds. And on Earth, phosphine is a byproduct only of some industrial plants or bacteria. Now, there are no industrial plants on Venus. So the likelihood is it's bacterial, if that's real. And again, we need more investigation. So in summary, no evidence of intelligent life. But there's so many planets in the universe, it's very likely. And there's no definitive evidence of any life in either our galaxy or the solar system. But we're beginning to get data to support this. There's lots of planets and moons with habitable conditions. There's some possible evidence of current life on Venus. There may be even current life on Mars. Even though it's ancient, Mars also now we know has liquid water below, for example, the ice caps as well as below some of the regular rock on Mars. And so if that's true, Mars might have life living there now, since it had life long ago. Same thing, Venus could have life on it. We now think that K2-18b could have life. So no definitive evidence, but lots of things pointing to it. And my opinion is that NASA's opinion, but mine, that we're likely to find that life within the next 20 years. Questions?
Okay, so you have 360 degrees around us of planets and solar systems. How much of that has actually been explored with telescopes? Any idea? 1% maybe?
Oh, a lot less than that.
Okay, great.
If you're talking about explored how, I mean in terms of like looking for exoplanets and habitability and life, as I said, there's only been about 5,500 that have been explored, and not all of them in depth. So yeah, tiny percentage.
Okay, one more question. Since we still all believe in the Big Bang theory, if there was a Big Bang, isn't there a big empty void out there somewhere? A big hole in the sky someplace?
So the Big Bang, it sort of expands from that one place. And remember, the Big Bang was a singularity, so basically without any mass or dimension. So where the Big Bang happened was less than an atom of size. So yeah, there is a void, but it's about an atom of size.
I wonder if how important the oxygen for life. Oxygen, O2.
Oh, well, not all life needs oxygen, remember. There are anaerobic bacteria that exist without oxygen. So it's possible, and there are bacteria that use the materials around them and excrete oxygen, so that can put oxygen into the water. I mean, we know that we're now thinking that at least some life became present down at those hydrothermal vents, and there's no oxygen down there.
I wanted to know, do you have any theories of why Mars doesn't have life anymore?
Well, we don't know life doesn't have life.
Or
We
why
don't-
it dried up?
Right. Why did Mars water dry up? They're beginning to think that basically Mars right now has no magnetic field. They're beginning to think that Mars did have a magnetic field and somehow lost it. And when they lost it, then basically their atmosphere disappeared. When their atmosphere disappeared, obviously the water disappeared too. But no one's really sure about why exactly. And that's one of the things that's being explored.
You didn't discuss the moon at all.
The moon.
The moon.
I didn't discuss the moon at all. I didn't discuss the moon, our moon, because there is ice at the poles of the moon, but the moon has no atmosphere at all. And we don't think the moon has any kind of ocean below its surface. The moons that we're talking about, like Jupiter and Saturn, have this ice crust that is able to preserve an ocean below them. Notice that those moons have no atmosphere. So anything on the atmosphere would boil off. But what they do have is that ice crust preserving what's below it, which are these huge oceans. The moon doesn't have any of this crust. So there isn't any liquid water that can be preserved below, inside. The only other place would be at the poles, and that's all frozen ice, not liquid water.
You know, they have brought up objects from those vents and how similar they are to what we find in the surface and how they're different.
Yeah, so the question was, do I know, you're talking about the vents on Earth, because we haven't explored the vents on Jupiter, on Europa. The vents on Earth, yes, they have been explored. They have brought up stuff. About 2/3 of it is you're able to directly relate it to something on Earth. About 1/3 of it, you can't, you see nothing else on Earth like it, which means it either drifted down somehow on its own and nothing relates to it on Earth, which doesn't make sense, or it formed like that. And that's the likelihood. And so about a third of the different species that are there. Which ones? I can give you an example. There are these tube worms that are down there. Nothing else like it on there.
Is there a chance that it might define life other than our carbon, hydrogen, oxygen chemicals? I mean, no doubt on the beds. On the beds, some of them anaerobic, don't you?
Right. Anaerobic, yes, but there's still carbon, hydrogen, nitrogen, sulfur, phosphorus. Life that is not carbon based has always been sort of a hypothesis of science fiction. If you the original science fiction, the original Star Trek had an episode with the Orda, which are these silicon based life. The problem would be the amount of energy needed to support something like that, and why would they form in a less than optimal environment? But yeah, it's possible. Right now, we're looking for any kind of life. So if that pops up, yeah.
I think, talking about Europa, you said, besides the volcano events, there was organic man-made surface and speak that out.
Yes. Yeah, how it was determined was based on the spectrography from some of the missions like Juno that flew by, or whenever it was examining Jupiter, and they found carbon on the surface. In terms of how it happened, if you're having these vents that are spewing out water, the material and some of the stuff on the surface is also, a lot of stuff on the surface is also just mantle, not carbon based, just mantle. But any of the particles that are either mantle or carbon based are going to settle out and fall back onto the surface.
Efforts to study those meteorite samples for life, carbon-based residuals.
No, I did not plant that question. I'm glad it was asked. Yes. So far, we have Osiris Rex bringing back matter from new. They have not done a thorough evaluation yet. The only thing we know is that there was a lot of carbon-based material. What carbon-based material we don't know yet, because they haven't done a full spectrographic analysis. There was a small amount of matter brought back, only 5 grams, excuse me, brought back by a Japanese probe called Hayabusa 2 from an asteroid called Ryugu. On there was a lot of carbon-based material. One of the things they found that they recently reported was a fair amount of uracil. Now, if anybody remembers their high school biology, uracil is one of the bases of RNA. Okay, DNA has a different, a base that's not uracil. I forget which one it is. Cytosine, I think, in place of uracil. But RNA has uracil. And it's believed that the original life on Earth may have been RNA-based rather than DNA-based because it's simple. And now you have an asteroid bringing back material from deep in space where it's been 4.6 billion years that has uracil on it. Why not have that hit the Earth some 3.6 billion years or more ago and populate the Earth? And that's probably how life started on Earth. So yes, we're doing a lot of investigation about that.
I read where NASA's having issues with regard to the retrieval of those samples on Mars. Issues in the sense of maybe getting ahead of themselves with regard to the technology necessary to go over the back on Mars, gather that material, send it off Mars, get it to a lot of the station, send it back to Earth. And the issue was the technology and the time related, the timeline being expanded out several years.
The main issue is money.
Money.
With enough money, NASA would be able to develop the technology within a short period of time. But NASA has had its funding cut.
Great stuff, Neil.
Well done.